So here you have a picture of Einstein, and each one of these is a different octave. It's cut in half, cut in half, cut in half. And then you can see we go from crisp to blurrier to blurry to blurry. It's probably the only time Einstein was fuzzy in his life. And then, just as we showed in this picture before, we can subtract, example, these two and get that difference, all right? Or we can subtract these two and get that difference, right? So these are our difference of Gaussian images. And then what we can do is we can take each pixel in one of these and compare it to its neighbors in space and its neighbors in scale. And when you do all of that, you can find the extrema, and it looks like that. So this is an Einstein picture with really bad dots. But some of those extrema might be higher than their neighbors, but not very high. This happens in Colorado. So you want to make sure that the contrast or that value is higher than a particular amount. So we say, aha, here are places with contrast. But we say, wait a minute. We said before that when we use Laplacian and Gaussians, we might have nice contrast, but it might be high just in one direction, so along an edge. So what do? We remove the edges, and voila, these are our detectors. Okay? And what's important here is these are detectors that are robust with respect to scale, because we pulled out all the extrema at all the different scales. And this was David Sift detector. So this can be written sort of like this. So for scale invariant detectors for SIFT, here we've shown that you're going to do difference of Gaussians in space and difference of Gaussians. You're taking all these different Gaussians and comparing them in space and in scale, and you're picking the maxima. And here's a reference from, again, the journal Computer Vision, where he talks about this. There is another approach that's quite related. It uses both things that we just talked about. First, you essentially do the Harris corner detection at lots of different scales. And then you also take a look at the Laplacian in the scale direction, and you find points that are the maximum in space in the Harris measure, right? That's like that non-maximum suppression, and are maximum in space, in scale, in the Laplacian direction. And this is sometimes called the Harris-Laplace detector. The paper here, ICCV, is one that's referenced. And you know, I can show you, here's a nice little demonstration that with change of scale, that, well, first you can see the original Harris detector, in fact, does really poorly. That's what we saw before. The SIFT detector, that's the thing in the green line, that was the thing we showed you before, it does way better than the Harris detector, but along comes Harris-Laplace, and it does even better. And so you might say, well, of course we should use Harris-Laplace. I will tell you a lot of people do. I will also tell you that this graph comes from the people who invented Harris-Laplace. So, you know, your mileage may vary.